Hello class, and welcome to section 8.5, which is about linear, quadratic, and exponential models. By the end of today's lesson, you'll be able to determine which of those three models best suits a particular set of data. So in order to do this, we're going to look at a couple different things. The first thing that we're going to look at is called the first difference. So that means the difference between consecutive y values in a data set. So we're looking to see the difference, so the subtraction between the y values. One thing to note is that it has to be a constant difference between the x's for this to work. So -2, -1, 0, 1, and 2, we're all going up by 1. If this was -2, -1, 0, 2, and then 4, so something changed in what we were counting by, we would not be able to validly say what model would work because we would not have a consistent set of data. So we're going to use these first differences, and this is to determine if it is a linear function. So what you would do here is I'm going to just add another column here. So my first difference would be to say, all right, 1 minus -1, which is going to give me an answer of 2. And then I would look and I would say 3 minus 1, which is 2. Then 5 minus 3 is also 2. 7 minus 5 is also 2. So because all of these values right here, these first difference values are 2, we would say that this is a linear model of data. If you got answers like 2, 2.1, 1.8, and 2.1, that's fine. They're all close to 2. So all of these values should be roughly consistent, and then it's going to be a linear model. The second difference is going to be looking at the difference between the consecutive first differences. Again, our x values have to be constant, so we have to be counting by the same thing as we go up, and we have to find that first difference first. So to get from 3 to 9, we went up by 6. 9 to 19, up by 10. 19 to 33 is up by 14. 33 up to 51 is 18. So those first difference values are not the same, so it is not a linear model. So then we're going to go ahead and look at then what we're going to call the second differences. So that's how we get between the first difference values. So from 6 to 10, we went up 4. From 10 to 14, we went up 4. From 14 to 18, we went up 4. So those are our second difference values. If your second differences are consistent or roughly equal, then we're going to say that this is for a quadratic function. So something with a power of 2 as the exponent. So this is going to be a quadratic function. The last thing is the y value ratio. So the ratio or division between the consecutive y values in a data set is constant. Again, has to be consistent x values. 1, 2, 3, 4. We're going up by ones. When you're doing this, you're going to want to first check the first difference values, which I calculated here for you. So going up by 1, then 2, then 4, then 8. And then we would look at the second differences. 1, then 2, then 4. None of those match. So now for the last part, we would be checking the y ratios. And for that, we're going to look here and we're going to say, okay, the first 2, we're going to say the ratio is 2 divided by 1, which is going to give me 2. So the y ratio, 2 over 1. The next ratio is 4 over 2, again, giving me 2. The next ratio, 8 over 4, which is 2. And that last ratio, 16 over 8, which is 2. So because then these y ratios are consistent, 2, 2, and 2, again, or something very close, such as 1.9 or 1.8, that model is going to be best suited by an exponential function. So we can use first and second differences and the y value ratios to determine which model best suits. So if they give us the data set negative 2, 4, negative 1, 12, 0, 36, 1, 108, 2, 3, 24. My first job is going to be to determine what type of model we want and then explain my reasoning for that. So I'm going to start by calculating the first differences and see if it is going to be linear. So if I calculate my first difference, 4 to 12 is 8, 12 to 36 is 24, 36 to 108 is 72, 108 to 324 is going to be 216. So my first differences don't match, so it's not linear. Then I'm going to go ahead and check my second differences. To get from 8 to 24, 16, 24 to 72 is 48, and 72 to 216 is 144. Again, those don't match, so it is not a quadratic function. So that last thing I'm going to check then is my y ratios, and I'm going to say, all right, 12 divided by 4, and that is going to give me 3. And then for the next one, I've got 36 divided by 12, also gives me 3. And then I've got 108 divided by 36, also gives me 3. And then I've got 324 divided by 108, and that also is going to give me 3. So since my y ratio is the one that is consistent, I would say that this is an exponential function. So I would say what kind of function it is, and then I would say because the y ratio is constant. So you have to say what type of function it is and which one of those three things tells you that. Go ahead and try this one on your own. So you can see my first and second differences. And when I get to the second differences, it is quadratic. So technically, you did not have to do the y ratio part. I just put it out there to show you that it does not work, that the only one that's consistent is the quadratic. But once you got that quadratic answer, you did not have to actually show the y ratios. The other thing that we're going to do is compare the three different types of functions. So we have three functions that are being used to model the population growth for three different cities. Let f of x equals 3.2x, g of x equals 0.25x squared, and h of x equals 2 to the x minus 5 power. How long will it be until the city modeled by h of x has the greatest population? So it's basically asking us to do a bunch of solving until h of x gives you the biggest answer. My recommendation for this, take it in chunks of 5. So I'm going to look at x equals 1, 2, 3, 4, and 5. And I'm going to evaluate that for f of x. And I'm also going to do it for g of x. And I'm also going to do it for h of x. So we have all of those different models that we're going to be looking at to find the answers and see if and when h becomes the biggest. My recommendation, plug all of the x's into one function at a time. So if I go through and do f of x and I plug in 1, I get 3.2, 2 is 6.4, 3, 9.6, 4, 12.8, and 5 is 16. Then I'm going to go through and do the same thing. So plugging all of 1, 2, 3, 4, and 5 into g of x, I'm going to get 0.25, and then I get 1, and then I get 2.25, and then for 4, I get 4, and for 5, I get 6.25. Then I'm going to go ahead and plug all of those numbers into h. One thing to be careful about with this h is when you type it into the calculator, it would be 2 caret, and then for the first one, 1 minus 5 is in parentheses. So if there's any parentheses in these equations, you're going to want to make sure you're typing those into your calculator. So you end up with here 0.0625, and then 0.0625, 125, and then for 3, 0.25, for 4, 0.5, and for 5, 1. So far, f of x is still the biggest one, and I want h of x to be the biggest one. So I'm going to go ahead and I'm going to look at another group of 5. So I'm going to say 6, 7, 8, 9, and 10. I should note you always want to start at 1 when you are comparing these because our functions are moving from left to right and all of them are getting bigger. There is no negative. If there was a negative 3.2, negative 0.25, and negative 2 as that last value, then you would be going the opposite. So starting with negative 1, negative 2, negative 3, etc. But if your coefficients here are positive, you're going to be plugging in the positive numbers to try and find when h takes over as the greatest. So now we're going to do this next group of 5 once I'm done setting up my table. Obviously, I on the smartboard don't want to extend my page down so long. If you are making a table and you want it to just keep going down, as opposed to me where I'm making multiple tables going across, that is fine. Again, I recommend plugging into one function at a time. So I'm going to start with that f of x function. For 6, I get 19.2, 7, 22.4, 8, 25.6. Put that point in there, 25.6. 9 is 28.8. And 10 is 32. Then I'm going to plug into g of x, so into that second function. And I get an answer of 9, and then for 7 is 12.25, 8 is 16, 9 is 20.25, and 10 is 30.25. And then for h of x, I'm going to get 2 for when I plug in 6. We get an answer of 2, and then 4, and then 8, 16, and 32. So right now, I am very close. H of x has taken over g of x, but it is still under f of x. So I'm going to go one at a time now that I've gotten very close. So I'm going to go ahead and I'm going to plug in 11 into each of the three functions. So f of x, g of x, and h of x, I need to plug 11 into all of those. When I plug 11 into f of x, I'm going to get an answer of 35.2. When I plug it into g of x, I'm going to get an answer of 30.25. And when I plug it into h of x, I'm going to get an answer of 64. So at that point, h of x has the biggest answer, so I can stop because I wanted h of x to have the greatest population. So then my final answer would be after 11 years, h of x has the greatest population. So you would make a comment to say what happened at that time. So h of x, again, has the greatest population after 11 years. Now we're looking at 3 different models to project sales growth. We are wondering how many years until the exponential model has the highest sales. Go ahead and try this one on your own. So when I do that, I'm going to plug in. Again, I recommended going in groups of 10. So in these first 5, that exponential function, the h of x, is not the biggest. As I keep going then, once I get to 7 years, that exponential model is the greatest, so I wouldn't have to fill in those last pieces for the exponential. So after 7 years, h of x is the highest. If you have questions about this or anything else from the lesson, please let me know when you get to class.